every time. You want the recording at the end at least. So there will be no recording of the disk part, but still, let me just. So you can see my screen again now.
Yes, sir.
Okay. So I was just trying to give you a reminder of the way in which you derive the formula for the current. This is the volume. The number of particles which go in is the density into the volume. And this NV vector, this is what you call your current for particles. You wanted current for charges, we have to multiply this by the charge per particle. This is where the NEV comes from. Okay? So this should be pretty familiar to all of you. All I'm saying is, in the two-fluid model, which Tisa and London had introduced, you could think of the fluid helium-2 below its transition temperature as composed of a superfluid and a normal fluid. The density of the particles partly will be superfluid, partly will be normal. And the current, which talks about the movement of the fluids inside, which of course is what we have to talk about, right? We are talking of flow. And we'll have both a superfluid part and a normal part. And using this model, Tisa and London tried to explain the various. Just hold on. Okay, hold on. Somebody's calling me. Okay. So what Tisa and London had to do was explain all the phenomena that we have been describing, and they did a pretty good job of that using this two-fluid model. One point was, why did they believe there are two fluids? Because they thought that this was the same phenomenon. This helium-1 to helium-2 transition was the same phenomenon as Bose-Einstein condensation, which had been sort of theoretically predicted by Einstein a few years ago. And just like in Bose-Einstein condensation, you have a normal part and a condensate part and a non-condensed part. They said, okay, you are going to have the condensed part. The Bose-Einstein condensation will occur. The condensed part will be superfluid. The rest will not. Now, at this stage, another major actor enters into our story. So we are back to the history once again. And this is rather fascinating, this part of the history. This person who enters our story is Lev Davidovich Landau. Okay. I'm sure you must have heard his name in some other context. Have you? Yes?
Yes, sir.
Why do you? There may be several reasons to know his name, if nothing else, because he is one of the co-authors. He was a major author. Actually, he is the author, the other one people primarily edited. Uh, some of the best known books, or series of best known books in advanced physics, the Landau-Lifshitz series. I'm not sure whether you have seen this. At least you may have seen at least two or three of these books, definitely. The Landau-Lifshitz series is one of those, really legendary things which physics uses. But apart from that, even in your course, you must have heard of his name in the context of phase transitions, right? Landau theory of phase transitions.
Yes, sir.
Okay. In fact, you could have, if you go into more and more advanced physics, you would see that he has contributions all over the place, not just in phase transitions or not just in superfluids, but And his involvement in Superfluid is actually is quite has quite interesting story behind it. It's quite a thrilling story as well. Now, remember, all this was happening in 1930, late 1930s, 37, 38, 39, and so on. So something very huge happened in 1939 in world history, right? You know what that is? Late in 1939, something began, a very big event in world history. What was that?
World War.
Yeah, the Second World War. Right. Second World War commenced in 1939. And this was just before that. So the things were pretty tense. Of course, war doesn't start just one fine morning, right? Tension was building up over quite some time. So remember these people, all who were working in superfluidity. You had Moscow, capital there, you had Leiden laboratory, which is in Germany, you had Oxford and Cambridge. So in all very different parts of the political game at that time, at least the politics of the countries were very convoluted. In particular, okay, okay, you must know who was ruling Germany at that time and who was ruling, okay, England, Germany, Russia, who were the heads of state. Okay, heads of state, England, you would always say is the king, but don't. I mean the prime minister for England. Who was he? These areas, 37, 38, 39. The leader in Germany and the leader in Russia, who were there? Seems like a completely unrelated question, but it's not real.
Germany, Hitler was there. I
Germany was
don't properly remember.
from
Was it
1933.
Mussolini or Stalin? Someone. Mussolini, I don't know.
USSR, it was
Stalin.
Stalin. Right. Mussolini was Italian. And England, you may not know. England was Neville Chamberlain just before Churchill took over after the war started. But anyway, our important features at that time, Stalin was ruling Russia and Hitler, of course, was ruling Germany. And both of them were very autocratic in their own ways, of course. And and Landau, who happened to be an Ukrainian, although at that time there was no Ukraine-Russia divide. Stalin also was not Russian, he was Georgian. And Georgia is not even in Russia now. But at that time, Landau, who was always a rather outspoken person, made a public statement that Stalin is as bad an autocrat as Hitler is and should be removed from power. Of course, in Stalinist Russia, saying such a thing out in loud, especially for somebody as prominent as Landau, Landau was already pretty well known at the time, meant that the regime could not ignore him. He was thrown in jail in 1938. So, and for indefinite time, 1938, then Landau was jailed. And not only jailed, it was sort of expected that he might even be killed in jail because of statements like this. Now, this was a time where Kapitsa, remember, was already well established in Moscow. After all, the Moscow government had pleaded with him to stay back and had given him all kinds of facilities, including all the money he wanted to build a huge lab, and he had already done a great job. He had discovered superfluid flow in 37, in late 37, early 38. And Kapitsa played a huge role here. What Kapitsa did was to tell the Russian government that you have to release Landau, because if you don't, the only person who can possibly explain this phenomenon that we are seeing, we will lose him. That is, he said there is nobody else in the world other than Landau who can possibly explain this new phenomenon that we are seeing. So if he is kept in jail or killed, all our work will be completely down the drain. Nobody will be able to understand what we are doing. This was a pretty bold move. Remember, at that time, saying something so. In fact, Landau was jailed just for saying Stalin is like Hitler and saying that I will that you have to release him. In fact, what Kapitsa did was say that if you don't release him, I'm simply going to stop working in science forever. So you will not get anything more from him. That was in itself a very bad, a bold move, because authoritarian regimes don't really take that well to threats like this. But Kapitsa was, after all, the golden boy at the time, and they had already spent a huge amount of money building his lab, and also he had actually really given them a return. So in 1939, just before the war started, Landau was released. This was essentially done because Kapitsa had sort of said, had threatened to quit working in science unless Landau was given freedom to both move around and work as he wanted. So 1939, that Landau got released. He was already interested in superfluidity before this, but right after his release, he started working earnestly in superfluidity. And the first thing he did basically was to take a look at the two fluid theory, which Tisa and London has given us. And well, he was not very impressed. He immediately came up with several reasons why the two fluid model, as presented by Tisa and London, cannot be correct. Note that he was not against the two fluid model. In fact, he built on the two fluid model, and he made a hugely successful phenomenological theory, much more successful than Tisa and London's, based on this idea. What he was objecting to was that what was being observed is Bose-Einstein condensation. Okay? So, why was he so against this? Well, one of the reasons was several reasons were experimental. One of them was this disk experiment that I talked about. Remember, the disk experiment kind of convinces people that you are going to get, or the disk experiment was actually done over quite a few decades in different degrees of sophistication. But it was already well known at that time what kind of results to expect. And basically, if this were BEC, so what could this thing do? You could, by measuring the time, you could actually figure out, measuring the time period, you could figure out how much of the helium-2 was actually superfluid, right? By seeing that as temperature changes, below, so this is Tc, this is temperature, this point is Tc. As temperature falls below Tc, the time period of oscillations change gradually, they decrease gradually. From that, you could figure out this much of the normal fluid is dropping out and becoming superfluid. And so if you just look at it, this looks very much like the BEC curve. So, sorry, I wrote this BEC here, but here I mean the superfluid helium over total fluid. And the BEC curve looks very similar, looks somewhat like this. Okay, if you, with my poor drawing skills, I cannot make out any difference. So this is N0 by N, condensate over total, and this is superfluid by total. And of course, N0 by N is this famous formula that we have derived several before and talked about several times. It's about 3 by 2, not 3. If I wrote 3 earlier, thankfully that has not been recorded. It's actually 1 by 3 by Tc to the power 3 by 2. I don't remember whether I wrote 3 or 3 by 2 earlier. But this is the formula we derived, right? Now, what people could do is actually make very careful measurements. Because frankly, this was not really that, well, that much careful experimentation was not available to Landau, although already people had got some inkling of the behavior of this curve. One thing that they measured was this gap. This, of course, is 1, which means all of it is superfluid. This gap tells you how much normal fluid is there, right? And experiments carried out near 0 Kelvin, not Tc, but near here, that is around this region, showed that the superfluid amount is less than N, of course, because some of it is normal fluid. And you have something like this. This is the behavior that they saw. That is, the normal fluid part actually went like 8 to the 4. Okay. This was experimental. Experiments did with oscillating disks inside superfluids, inside helium 1, helium 2, showed that the normal part actually close to the zero temperature, we had like a fourth power of temperature, which does not match what this shows. Okay. By the way, your task for the BEC, if you try to calculate that, if you believe that the BEC was actually what superfluidity was showing, and try to calculate the normal part from this formula, it's pretty easy, right? The norm Nn here will be simply n minus n0. Will be n into t by Tc to the power 3 by 2, right? So you can see the difference in the two formulas. The BEC formula is accurate throughout. This experimental result was only accurate close to t equal to 0. But you see, close to t equal to 0, this formula should still stay t by Tc to the power 3 by 2. So t to the 3 by 2, whereas experiments tell us it's t to the 4. Very different, right? Okay. So that was one thing which would immediately tell you that something is happening which is not exactly BEC like. And again, very close to this TC. So if I were to see what happens here when T is close to TC, the superfluid portion is behaves like this. Sorry, not T minus TC. T minus TC would be negative. Actually, TC minus T to the power 0.67. That's again experiments. Then convince yourself that close to this, close to T equal to TC, the behavior of superfluid will be, or sorry, BEC condensate will be quite different. Is it okay? You understand the point? So if you look at the details of how much superfluid part is there as a function of temperature, you see that both at very low temperatures and close to T equal to TC, the behavior is substantially different from a superfluid. Okay? From the, sorry, between a superfluid and a BEC. Any questions about this?
Yes, sir. At t is equal to 0 K, I mean, the equation was Ns is equal to, it was dependent on temperature as T to the power 4. And when T is
Right.
near
Not
TC,
at T is equal to 0K, of course, but T very near 0K. At T equal
this
to
is
0K,
for,
it would be 0. Right? Normal
this is,
fluid. This is for the helium 2 experimental. This is a normal fluid part of helium 2. T very near 0K, it's 8 into the 4. Okay, so go ahead. What was the question?
no, so that is what I wanted to ask. Was this superfluid or not?
This is, the normal part is 8 into the 4. The superfluid part is n minus that. Okay.
Yes.
This tells you that the normal part goes to 0 very rapidly as T goes to 0 as a fourth power of T. Whereas the uncondensed part in the BEC goes to 0 as T goes to 0, but as a 3/2 power, as to the 1.5 as opposed to the 4. Quite a drastic difference. And you can, okay, I will leave you as an exercise to figure out when you're very close to the thing, what does this formula, Nn, not Nn, but the formula for N0 by N, tell you about the behavior of N0 when T is very close to TC. You will get a TC minus T to the power something if you do the approximation right. But that number will be very different from 0.67. Okay. So the details, although on the face of it, the BEC curve and the superfluid versus total fluid curve in helium 2 look very similar. The details are pretty different. Okay. That's one thing. Although frankly, Landau wasn't really, didn't really have access to this much information when he was talking about rejecting the BEC notion for two fluid theory, because All this came out of very detailed experiments. It had only started in Landau's time, but much of it was done. Much of the things that we know about here actually was done after, was maybe in the 50s or 60s. The detailed values that you get. Okay. But Landau knew that even from the experiments at that time, there were differences between the BEC prediction and the helium 2 behavior. Well, another one, something which we have already talked about the other day, the sign that the superfluid transition occurred was, at least when it was first discovered in Leiden by Camerling's team, it was that at T equal Tc, they were essentially measuring heat capacity as a function of temperature. And they got something like this. At T equal Tc, the heat capacity diverged. That is, if you look at the formula for the heat capacity, notice that there is always a smooth variation and then there is a divergent part. The smooth variation is some smooth function of temperature. The divergent part goes like a negative power, right? When T is bigger than Tc is T minus Tc to the power minus alpha, negative power, because then when T goes closer and closer to Tc, T minus Tc goes closer and closer to zero, you get infinity, right? That's what happens. This is above Tc, below Tc also, that is above Tc also you get divergence. Below Tc you also get divergence. The two divergences are not identical. This one is slower, that one is faster. So the A minus is different. But you get this. This is what you get experimented. This is what Landau knew very well because this was already established around a decade ago in Leiden by Camerling's. Okay, the so-called lambda transition. Now, why was this something which Landau took to be against the idea of BEC? Once again, let me tell you that Landau did not reject the two-fluid model, but he used it, but he rejected the idea that this two-fluid is basically Bose-Einstein condensation. Why? Because in Bose-Einstein condensation, we had actually talked about this before. The CV essentially behaves like this. What's the big difference between this and this? These are two curves.
It doesn't diverge. CV doesn't diverge at
So
T
for
is equal to.
BEC, yeah, for BEC, CV doesn't have a divergence. It has a, it's in fact continuous. It just has a kink in the curve. The slope is discontinuous. Helium 2, on the other hand, or helium 1, this is not helium 2 alone, it's helium 1 to helium 2. Helium 1 on this side, 2 on this side. Shows divergence or in CV as T goes to TC is approached. Okay. So that was very different from what BEC would have shown. And that was another reason. In fact, that was one of the major reasons why, it's an experimental reasons rather, why Landau rejected the TISA-London proposal of BEC being responsible for superfluids. Okay. Right? Now, if you look at these equations, NS, this is what happens, this is the equation of what happens close to TC. The fraction of superfluid essentially goes like Tc minus T to the power 0.67. Heat capacity blown up like a power of T minus Tc or Tc minus T, depending on whichever is positive. A negative power in this case. Have you seen things like this elsewhere? This kind of power laws of behavior of things which either go to from zero to rise gradually or become divergent. Where else have you seen things like this, power laws like this come up? You have seen this definitely in physics. So, okay.
Phase transitions.
Exactly. You see this in phase transitions. Not only phase transitions, you don't see this in phase transitions, you see this in the part of phase transitions that you study the most, which is not necessarily the most common part, but you study it most because it's most interesting experiment in theoretical. Is the so-called critical phase transition. This kind of behavior happens at the critical point of a second order phase transition. Okay? So this pointed to the fact that superfluid transition, the lambda transition, the second order or critical phase transition. And of course, Landau had a one lot to say about critical phase transitions in his theory. We will come back to this aspect of the critical phase transition that happens in lambda transitions and look at the superfluid transition from the point of view of order parameters, things which we use when we describe phase transitions. But let me just quickly talk about the theoretical. These were experimental objections which Landau had to the VEC model of superfluidity. Let me talk about the theoretical uh, objection he had. And in fact, it's a beautiful argument that he gave, which was the idea of a critical velocity in superfluid flow. This was Landau's amazingly simple idea. In fact, it's one of those ideas which really takes a genius to work out. But once you know the idea, it would seem like it's obvious. But why didn't we think about it before? Okay? But in order to understand this idea, we will first need a bit of a background, something which you all know, or at least all can work out very easily. Suppose that I am observing a moving object. It has some energy, right? It also has momentum. Let's suppose that instead of me, somebody else who is moving with respect to me, another observer, is also observing the same moving object. Will she observe the same momentum and same velocity or same energy? So we are talking about the background idea now. Will an observer who is moving with respect to me observe the same energy of another particle, a third particle which we are both observing? Will we both see the same energy and same momentum? Or maybe same energy, different momentum, or different energy, different momentum? How does it go? Yes? Come on, this is a very simple question, right? Are quantities like energy and momentum dependent on the observer or independent of the observer? How do they change from observer to observer? Do they change or are they the same? Am I connected at all? Because this is a very simple question, I'm a bit confused that nobody's answering.
Sir, actually, your voice is cracking in between.
For a long time or just now?
So we couldn't understand the question actually.
Okay, the question is, two different observers, let's call them A and B, they're moving with respect to each other, let's say with the velocity v. They both observe some object in mass capital M velocity, some velocity, let's say v vector, with respect to A. Of course, this is measured with respect to A. That means the observer A sees that this system, this object, whatever it is here, it has some energy E, it has a momentum P. Right? Okay?
Yes.
Now the question is, when you're talking to the second observer, will the second observer see the same energy, the same momentum, or different energy, different momentum? Remember, A and B are moving with respect to each other. So, yes,
Different
will
energy
they see
and
the, sorry, could you repeat that?
different energy and different momentum.
Right, and how are they related? That's a question that we really need to answer. How are energy and momentum related when you change observers? Now, in relativistic physics, you already should know that there is something called the energy momentum four vector. There is the energy, is a zeroth component of four vector, momentum is a third component, is a spatial component. And therefore, in relativistic physics, we have a very simple way of figuring out how energy changes when you change observer. Basically, E by C and P transforms in exactly the same way as CT and R does. So if you know Lorentz transformations, E by C, P, how they transform, will be easy to do. But we don't really need the full relativistic picture because there's the kind of thing, the superfluid flow, for example, will not happen at light speeds. It will happen pretty fast, but at normal macroscopic speeds, not really speeds of objects like light. So non-relativistic formula will be fine. Now, so the question that we want to address is how does energy transform when you change one observer to another? Now, while there may be different kinds of energy, the transformation rule will be the same for all kinds of energy. Okay? So the transformation, so the simplest thing to do would you just look at kinetic energy. Let's say E is half mv square, right? Capital V. For the observer A, for the observer B, E prime will change. What will change if you are dealing with non-relativistic physics? In this formula for the kinetic energy of the particle, or whatever this object is, which factors will change? Will M change or will B change?
So V will change.
Yeah, the M will not change, V will change, and V will change according to a very simple rule, right? If V vector is a velocity as observed by A, then B will observe a velocity which is capital V minus small v, where small v is the velocity of B with respect to A. Is that okay? Standard relative velocity formula, nothing else. But now you can immediately expand this out and see that you get three terms on the square. Right? So E prime, the new E, the new value of the energy is the, or when I say new energy, I mean energy in this new frame is the energy in the old frame plus half capital M V square. This V is the velocity of one frame with respect to each other. Minus, now what is this quantity mv? Is the momentum as seen in the original frame. Minus P dot V. Right? So this is the way energy transforms. In fact, we figure it out by saying kinetic energy of a point particle transforms in this way. The transformation rule is the same no matter which part energy you're talking about. Whenever one observer sees energy and momentum as E and P, another observer moving with velocity V with respect to the first observer will see an energy of E plus half mv square minus P dot E. Is that clear? This is the non-relativistic formula. The relativistic formula actually can be obtained. In fact, the relativistic formula is actually simpler to look at. All these are square roots of 1 minus v square by c square. It's actually simpler in idea, basically, because energy and momentum form a 4 vector. So it's easy to see that when you change observers, so it's easy to see why the momentum comes in. When you change observer, the new energy depends not only on the old energy, but also on the old momentum. Okay, this has nothing to do with superfluid. This is just basic mechanics. Okay, how these things change from observer to observer. Now, what Landau did was something rather beautiful with this simple idea. He said, okay, let's take a look at a tube in which superfluid is flowing. Inside that, you have superfluid that's flowing. So, although Landau rejected the Bose-Einstein condensate idea of Pisa and London, he knew very well that this was definitely a quantum phenomenon occurring in the macroscopic world. Remember, very low temperatures are what is needed to show quantum phenomena. Because only at very low temperatures will the de Broglie wavelengths become large enough to sort of make particle clouds indistinguishable from each other, something we already talked about in the context of GC. So he knew that he was seeing quantum phenomena. He was also convinced that what he was seeing is a macroscopic quantum state. He wasn't objecting to that idea. He was objecting to the fact that it is a Bose-Einstein condensate. But you have a macroscopic quantum state, which essentially will be superfluid. And of course, the part which is not in that macroscopic quantum state, that will be the normal fluid. That was his basic idea. Now, what he talked about is this. Let's say you have a fluid which is flowing, and this is a superfluid which is flowing in the tube. Okay. Now, if this was entirely a superfluid, let's forget the normal part. In fact, if this were a very narrow tube, all that will flow through the tube would be the superfluid part. So this is in a single quantum cell state. Now, what will the tube do? The tube will try to. The tube is not perfectly smooth, so the surface of the tube has imperfections, which, as the superfluid travels through it, essentially gives the time-dependent disturbance or perturbation on the superfluid. Right? Time-dependent because as the superfluid moves, at different times it encounters different imperfections on the tube surface. So these irregularities which are there in any real tube, that will effectively behave like a time-dependent perturbation. Time-dependent because it's a fluid which is moving. And at different times, comes in contact with different imperfections. So what does a time-dependent perturbation tend to do? If you apply it on a quantum system, yes? If you take a quantum system which is in some state and apply a time-dependent perturbation, what does it try to do? Yes? The Walter study time-dependent perturbation theory, right? What is the thing that you calculate at the end of the day in the time-dependent perturbation theory?
The energy correction.
No, that's time-independent perturbation theory.
The rate of
Rate of transition from one state to another, right?
yes.
What a time-dependent perturbation tries to do is change the system from one stationary state to another. Remember, if a state were really stationary, there would never be any transitions. right? Transitions occur because although the states that you call stationary are eigenstates of a Hamiltonian, that's not the full Hamiltonian. On that Hamiltonian, you have to add this additional pieces, which are the time-dependent perturbations. And it's these which drive you from one state to another. Without those perturbations, stationary states would have been stationary states forever. And even an excited atom would not have de-excited. It's the perturbation which makes it de-excited. Okay? So here in this context, what's happening? You have a superfluid in a macroscopic quantum state, which is flowing. The time-dependent perturbation, which typically will be the ground state of the system. What will the time-dependent perturbation try to do? It will try to excite particles. So all the particles were in the superfluid are in the ground state. And the perturbation will try to excite some of these particles to other states. Okay? So you would try to get excitations. Is it okay? And that is the way in which the wall can influence the fluid flow. The way in which the wall can cause a damping on the fluid flow and make it slow down is by creating excitations and changing the state of the system, of the particles from the ground state to some other state. Clear? Is it okay?
Yes, sir.
Now, excitations in an interacting system. Remember, a liquid helium is an interacting system. Excitations in an interacting system, at least low-lying excitations, excitations very close to the ground state, they behave like particles, or they behave like approximate particles, which is why they are called quasi-particles. I'm pretty sure you have actually met quite a few quasi-particles by now in your course. Phonons you definitely have met, right? Phonons, so-called particles of quanta of solid-state vibrations. Yes.
Yes, sir.
In any other kind of quasi-particle that you have met in your course so far? Hmm?
No.
Haven't you heard of magnons yet in your course? Or maybe
Yes.
you will. These are also quasi-particles. These are not real particles, but they behave almost like point particles for most purposes. Okay? In an interacting ground state of the system is excited, the low-lying excitations are basically things which behave like particles. Okay? So, what Landau said was this. What will the perturbation caused by the tube try to do? It would try to create quasi-particles. And a quasi-particle is essentially like a particle. It is a momentum. And also it has an energy. Right? That's how much energy is increased when the quasi-particle has been produced. Now this energy depends on the momentum. And now this is where the important thing comes in. The dependence between energy and the momentum is different for different systems. It depends on the details of the interaction. Right? Is that okay? So phonons have one kind of, so this is basically the energy momentum relationship is also the same as the frequency wave number relationship, right? Because energy is related to the frequency and momentum is related to the wave number. And this is called the dispersion relation. Just like the omega k dependence is called the dispersion relation for ordinary waves. And this, of course, depends strongly on what system you're talking about. Different systems are different. Like if we were talking of free particles, which was the one which we talked about in BEC, the relationship between energy and momentum was very simple. What was it? It is very familiar. Some would argue others are simpler, but at least this is very familiar. What is the relationship between energy and momentum here? For a free particle, Non-relativistic free particle. The energy is purely kinetic. Because remember, there's a free particle, no potential energy. So what's the relationship like? Well, just because it's quantum etc. or something like this doesn't really make a difference. So very simple result which you have known since class 12 or even perhaps earlier. What is the kinetic energy of a particle?
P square by 2.
This is P square by 2. Exactly, this is P square by 5. So this is for free particles. Not for all particles, of course. There are other kinds of particles which have different dispersion rules. Okay. Now, this suppose this perturbation produced by the wall has been successful. It has managed to create a quasi-particle excitation. Okay. So in the frame of the fluid, this energy momentum relationship is something which is derived or defined in the frame of the fluid. Okay. In the frame of the fluid, epsilon P is a given function, depends on the system, of course. But this dispersion relation tells you what happens in the frame of the moving fluid. There is a frame fixed to the fluid. So in the frame fixed to the fluid, what you have is you have a before you are, so you already had some energy of the fluid, some intrinsic energy, let's call that E0. This was before excitation. And after excitation, and moment, of course, you had zero momentum, right? Remember, you are in the frame of the fluid. So the fluid is not moving in that frame. So there is some energy of the fluid, which is some kind of energy. I don't care what it is. Let's call that E0. After excitation, what will happen is this E0 will increase to E0 plus epsilon. And the momentum will, of course, increase from 0 to 2. Right? Now, both of these statements are actually being made in the frame of the fluid. This is not because the frame has changed that the energy has changed. Here the energy has changed just because you have created an excitation. The tube has produced a time-dependent perturbation which has created an excitation. Right? Clear? Now, what will happen when you see this from the point of view of the tube? This is where this beautiful idea comes in. You have a fluid flowing with velocity v with a tube, and this result is in the rest frame of the fluid. What happens in the rest frame of the tube? Remember, the tube is actually moving at a velocity with respect to the fluid, which is minus v, right? If the fluid flows through the tube with a velocity v with respect to it, the tube's velocity with respect to the fluid is minus v. And so, let me just remind you of our relation that we had worked out. How does energy change? E prime is E plus half mass velocity squared minus momentum dot P, right? So if you go from one observer to another whose relative velocity is v, this is how the energy changes. Now, can you tell me what will happen in this case? If you go from the fluid frame, where this was the energy before excitation, and this was the momentum, and after excitation, this is the scenario. So, in the tube frame, before excitation, and after excitation. Before excitation, what is the energy? You just got to use this formula. What is it? Remember, E is E0. All that you need is given here. You have a fluid which has total mass capital M flowing, and you are looking at this from another frame whose velocity is minus v, which is the first one. So what will you get as a before excitation energy in the tube frame? Just use this formula. What will come out?
E plus half mb square.
Just that, not E0 plus half. Let's be precise. E is E0 at that time, so E0 plus half mv square, right? The minus P dot V term is not there because there's no momentum. P is 0. In the fluid stream, P is 0 to begin with. What about after the excitation? After the excitation, this is the energy. In the fluid frame, in the tube frame, this is going to be your E. And now what will you get? Just look at this formula. Tell me. It's very simple. You just take this formula and put down the terms. What is E? After the excitation, what is E? E is this. Just put that down. E0 plus epsilon P.
0 plus half mv.
Then plus half mv square. This mass is still the mass of the fluid. That has not changed. Of course, this V square should be minus V whole square, but minus V whole square is the same as V. And what about this term? Note that after excitation, momentum is not zero in the fluid phase. So this term will be there. So what will that be? Yes? Come on. Momentum is P. What is the velocity V? Velocity. Is it V or minus V? Remember what I need to put in this velocity here is the velocity of the primed frame with respect to the unprimed frame. In our case, the unprimed frame, the original one, is the frame fixed with the fluid. And the primed frame, the new one, in which I'm calculating E prime, is the frame fixed to the tube. So what should this term become? Yes? You just have to use this formula. Sorry, well, could you just repeat that?
माइनस भी होगा
मैंने V8 जगह minus V होगा. That's what you're saying, right?
So prime frame
हाँ
has
मैंने
velocity
क्लास
minus.
Prime frame velocity minus V ক্ষেত্রে অরিজিনালি ছিল E এর A আর B এর মধ্যে প্রাইম এটা হচ্ছে আনপ্রাইম ফ্রেম বিটা হচ্ছে প্রাইম ফ্রেম the prime frame had a velocity V. In our example, when V is the velocity of the fluid with respect to the tube's velocity with respect to the fluid. Remember here, the unprimed frame, the original frame is the fluid, the prime frame is the tube, so that will be a minus sign. So that's all. You'll have this. It's a minus P dot V, you'll have plus P dot V simply because V has to be replaced by minus. এইটুকুই। যদি খেয়াল করো অ্যাকচুয়াল ক্যালকুলেশনটা কিন্তু প্রায় ট্রিভিয়াল, কিছুই নেই। You just need to know the transformation rule for energy, which is very easy to figure out just by looking at kinetic energy. And then this works for all energy, and that's what we did. All the total energy of the superfluid was E0 before, had no momentum. Remember, we are talking about the fluid frame. Then, of course, the fluid has no momentum. After excitation, you have an extra quasi-particle, so the energy has gone up by epsilon P, and the momentum has changed from 0 to P. This was again in the fluid frame. In the tube frame, before excitation, you had this. After excitation, you have E0 and half mv square, but you have this and this extra. So how much is a change in energy because of the excitation as seen in the tube frame? That's simple. That's simply epsilon P plus P dot V. Right? তাই তো বাকি সবটা তো আগেও তো এতটা ছিল, এটা তো আগেই ছিল, এই দুটো আগে ছিল। This is what the increases. Now, this is where the physical insight by Landau becomes very important. He said that in the tube frame, the energy of the moving fluid cannot increase because of the perturbation. If there is going to be an excitation, that excitation has to cause an overall decrease in energy in the tube frame. In the fluid frame, of course, there was no quasi-particle before. Now you have created a quasi-particle with an energy. The energy has gone up. That will happen. That will happen. Definitely in the fluid frame. But in the frame of the tube, if it was possible for the tube to create a perturbation, which would create excitation that would increase the energy, then of course the tube could keep on producing energy, more and more energy, just by keeping on perturbing the system. That would actually be against the conservation of energy. You could create as much energy as you wanted. Or see it from another point of view. If this is going to be, if the job of, why do we say this is exciting? Why do we need this excitation? We need this excitation to take the system, the fluid, out of a superfluid state. That is, we need this excitation to produce a damping, right? Now, if it's a damping, then the energy should go down. Is that clear? In the frame of the tube, which is a tube, the energy of the fluid cannot keep on increasing. In particular, if the tube is going to damp the fluid flow, that is, destroy superfluidity in some way and create damping, the energy can only go down. Do you understand that? Yes? If the aim of the damping, yeah, hello? Was I cut off or something? Or someone wants to join the Anaka, have you managed to come in? Well, just a question. Anagar Prasad, right? Are you logging in from the ID that I sent you, that you sent me?
Yes, sir.
But then you shouldn't have asked for permission. Why is it asking for permission? You were there in the list, right?
Yes, sir, I was there.
Did they invite? You're sure you're logged into that account or not somebody else's, some other account?
No, sir. So even
That's
I don't know,
strange.
even I got a notification. I was there in the class previously, but when I just left and rejoined again, it was showing that someone has
Well,
to
that's
let you
strange.
in.
That shouldn't happen. That shouldn't happen. That is, first of all, if you were already in the class, next time you join from the same account, you would be allowed in automatically. You wouldn't have to wait for a notification.
Yes, sir, I was there in the class.
You were there. I noticed that. I thought that you had switched to some other account, perhaps. That might happen sometimes because people have multiple Gmail accounts, and that causes a problem sometimes. So just make sure that you're trying to join from the same account, the one with the
Yes, it's the
original.
same account.
So I can't understand why that happened. Anyway, it shouldn't happen, but anyway, it has happened. Let me go back to what I was saying. The point is, if the tube can cause a quasi-particle excitation which increases the energy of the system, which is the tube, that would actually violate the conservation of energy principle, in the sense that the tube can keep on doing it and get more and more energy out of it. So in order to be able to create a quasi-particle excitation, this must be zero, less than 3. In other words, a quasi-particle can be created in the fluid, in the moving fluid. Fine. It's just a fluid, it will have a positive energy, it will also have a momentum. But with respect to the tube, this quantity, this increase in the energy because of the quasi-particle creation must be negative. The energy must go down because of quasi-particle creation, not go up. And that also obviously ensures that you are damping out the system. So this is the condition for quasi-particle creation, which is also obviously the same thing as destruction of superfluidity, of superfluid flow. If a quasi-particle is created, that is going to essentially lower the overall energy of the fluid and essentially damp out the motion, decrease the energy of flow. So this is a very simple argument, really. All that was needed was how energy transforms from one frame to another, just this law. This is what is happening in the fluid frame. Whatever energy it had was increasing by the quasi-particle energy epsilon p, and that of course had a momentum. You just look at this from the tube's frame, you must have this quantity, these quantities. So the increase in energy in the tube frame can be zero, can be negative, can never be positive. That's the whole point. But now comes something very okay, very obvious, but also very useful. Can you tell me from this equation? Remember, epsilon p is the quasi-particle energy, which is a positive number. What does this tell you about the relationship between P and V? V is, of course, the velocity of the superfluid flow, right? P is the momentum of the quasi-particle which is created inside the superfluid. And that's the momentum with respect to the superfluid. What can you say about P from this? Yes? I'm asking a very simple question. If this thing is to be negative or even zero, what does it tell you about the relationship between P and V? Well, the most obvious thing it tells you, first of all. Firstly, P dot V. What sign should it be? Should it have? Yes?
Negative sign.
Right. That means the quasi-particle in the fluid's frame, of course, the fluid is not flowing. But in the tube frame, the fluid is flowing in this, say, to the right. Then in the fluid stream, the quasi-particle must be created to the left, not necessarily directly to the left, but making an obtuse angle with this, right? That's number one. Number two is, what can you say about the velocity of the fluid or the size of the velocity of the fluid? What is the largest possible negative value which P times V can have? P dot V can have? Simple, dot product of two quantities. What's the smallest value it can have? That is the largest negative value it can have.
-1.
-1. -1 would be true for two unit vectors. If you say -1, I guess you mean cosine theta can be -1, right? The dot product of P and V is magnitude of P times magnitude of V times cosine theta. The smallest possible value you can have is -1, right? So the important point is the speed. Okay, momentum of the quasi-particle created is against the velocity. So this thing is negative. Let's live with that. Otherwise, the so that is quasi-particles cannot be created moving in the direction in which the field is flowing. But then, what is the maximum possible magnitude this can have? That's magnitude of P times magnitude of V. The smallest negative value it can have is minus that. And now, this gives you a very important result, which is not the limit. We take this ratio, epsilon P by magnitude of P, which depends, of course, on this relation depends on what kind of dispersion relation the system has. So this depends on the system. And if you minimize this over all possible momenta, right? You take epsilon P by mod P, take this ratio, take the smallest possible value that you can get for this ratio. If mod V is less than this, then this quantity simply cannot become negative, right? Remember, you are adding two things. This is already positive. Unless this thing has a magnitude larger than this, unless this thing is negative and has a magnitude larger than this, you will never be able to satisfy this condition. So this is the criterion for quasi-particle creation. But if this happens, if V is less than this minimum value, then no quasi-particle creation can occur. Simply because it would be impossible to satisfy this condition. And hence, superfluidity will persist. Is this argument clear? To break superfluidity down, this quantity has to be negative. And that cannot happen if the magnitude of the velocity is smaller than epsilon p by mod p, the smallest possible value of epsilon p by mod p, then quasi-particle creation would be impossible. Okay? So this quantity has a name, it's called the critical velocity. If mod v is less than the critical velocity, in other words, if the superfluid is flowing slower than the critical velocity, then the tube cannot produce, tube's damping cannot produce quasi-particles. So the tube perturbation that the perturbation which the tube exerts on the flowing fluid will not be able to produce a quasi-particle, and there will be superfluid flow. If, on the other hand, the velocity exceeds Vc, then it will be possible for some momentums, some values of p, that is, it will be possible to produce some quasi-particles by excitation, and therefore you will begin to introduce damping. You will not have only superfluid, you will also have non-superfluid in the mixture. Is this part clear?
Yes, sir.
So finally, let me just quickly end this by showing why Landau was so against non-interacting BEC, the kind of BEC that Bose-Einstein condensation that Einstein had actually talked about. Why he was so against that being a possible superfluid? He actually managed to show, using his argument about critical velocity, that a non-interacting Bose-Einstein condensate can never be a superfluid, for the simple reason that for a non-interacting superfluid, this is what the energy is. Remember, these are free bosons, non-interacting particles, just the kinetic energy, right? So what is the minimum value of epsilon p by p? From this graph, it should be easy to say. Okay, so this is E, of course. When you are plotting epsilon p by p, what is the minimum value? In this graph, what is the minimum value?
0.
What is it? What is the minimum possible value for p by Poisson according to this graph?
The 0.
Which means the critical velocity for a free BEC is simply 0. It means the moment you have a fluid flowing through a tube, the tube will be able to produce quasi-particles in the fluid, and it will take the system out of the ground state. You will not get superfluid. Okay. So Landau's argument was actually quite beautiful. All he showed was you must have a criterion for superfluid flow to occur. The velocity of the superfluid flowing through a tube cannot exceed a critical velocity, which depends only on the dispersion relation. It's nothing but the minimum value of epsilon p by p. Just take that. So you take the minimum value of epsilon p by p or all possible p, you get the critical velocity, and that gives you 0. For the free particle Bose-Einstein condensate. So this was Landau's major argument against the Tisa-London theory, that Bose-Einstein condensation was occurring in superfluidity. He said that that's impossible, because if you make a Bose-Einstein condensate using free particles and try to make it flow through a tube, you have such low light like excitations available that the tube will always be able to excite those excitations or these quasi-particles and will take your system out of ground state and there will be the superfluidity will vanish. So you understand this is a very, very simple argument. There's hardly any advanced physics here, just energy momentum transformation. That's it. Now, on the other hand, Landau knew fully well that the free particle uh, dispersion relation is, of course, just one example. There could be many other kinds of dispersion relations depending on the interaction. For example, it was pure phonon. Do you know what the FNP relationship looks like? In a phonon-based system, it looks essentially like this. It looks like a straight line below, and then this is the so-called acoustic mode. It looks like a straight line because very low energy excitation or very high frequency, very low frequency or very high wavelength excitation see the solid almost like a continuum. So you get to see sound-like behavior. You must have studied all of this, right? Lattice vibrations and all that. Phonons, lattice vibrations have done this in condensed matter, right? Yes? Haven't you? You need to know. You've done this, right? And for phonons,
Yes.
the phonons, for phonons, epsilon is like proportional to P. Oops, sorry. Epsilon is like proportional to P for low frequencies, for there is low momenta as well, low energies. And as the energy grows, the momentum rises and you get closer to the edge of the Bilois zone, the thing curves. This is like the sine curve, Mott sine curve that you must have studied about in the phonon dispersion relation. Now here, in a curve like this, if you were to calculate epsilon by P, say at this point, this epsilon by P quantity, can you tell me what does this mean geometrically? The value of epsilon by P? Okay, if I were to join this point to the origin, to 0, 0 by a straight line, that's what I did right now. I hope you can see the great straight line that I drew. Right? Let's make it red and thick. This red line. What is epsilon by P with respect to that? Come on, epsilon is the y coordinate, P is the x coordinate here in this graph. Ratio between the two, what does it give you? Standard geometric question. Ratio between the y coordinate and x coordinate. What is the geometrical?
So slope of
Increase the slope.
Of what? Right, it's a slope. Slope of what? Yes? Hmm? Yes? Tell me. It's not the slope of the curve, it's the slope of this chord, right? And the slope of this red line, not the slope of the epsilon p curve. That's of course d epsilon dp. What we have here is the slope of this line. So what is the minimum value for this slope? In this case, the minimum value is achieved here, right? At the edge. At the edge of the below zone, you get a minimum value. If V is smaller than this minimum slope, there will be superfluidity. If it's larger than this, you'll get excitation. Now, I will just finish today's thing with two things. One is, Landau was able to show, in fact, Feynman was able to show later that, not really Landau so much, Feynman actually built upon Landau's work, and he managed to show that Bose-Einstein condensation can actually work here. Only it will be Bose-Einstein condensation between interacting particles, not non-interacting particles, which is what Landau had objected to. And he also managed to show that for a large variety of interactions, the dispersion relation actually looks somewhat like this. It rises up like the Phonon case, straight line, but then then you get a dip and you get a parabola-like behavior, which is basically because of a new kind of quasi-particle which is produced called the roton, which, okay, don't worry about that right now. But basically, this is what epsilon p versus p graph is. In interacting systems at very low temperatures, the ones which you see, at least this is the heliums. For things like helium, this is what you get. And then, what he managed to, of course, explain is the minimum for this one will be this, the slope of this line, right? If you take a point on the curve and join it to the origin, the minimum slope will be for this one line, which goes to the bottom of this pit. And for this, whatever epsilon 0 p0 this point has, the ratio, this is the minimum possible, and this is the OBC. Anything smaller than this, that is, if the superfluid flows slower than this, it is going to flow without damping. Only when the superfluid flow exceeds this, that will you get damping, and superfluidity will be destroyed. So contrast this with the pre-BEC case, where the dispersion relation is like this, which means no matter where you take your point, the slope can be made as small as you want. It can be made 0 in them. And therefore, for free particle BEC flowing to a tube, you will always get excitations. You will always destroy superfluidity. For a real interacting object, like in helium, the dispersion relation looks like this. And the actual physical origin of this is not really of our concern right now. But the dispersion relation, given that, we can figure out what the critical velocity is by looking at this line. Essentially, that's a line the least possible slope which will still intersect with the curve. Any line with smaller slope will not intersect the curve, and hence will never be able to produce. Okay, not intersecting the curve means the V will be too small. You have a P dot V which is large enough to exceed epsilon P in magnitude and cause excitation. Is this clear?
Yes.
So next day we are going to take a look at what Landau's theory and the more modern versions, of course, also of the theory behind this. Okay, I did say this was the last thing, but let me just add 2 more points. This is again back to history. In 1962, Landau got the Nobel Prize. He got the Nobel Prize for his explanation of superfluidity. In a sense, of course, the work was done in the 1939-1940. He got the Nobel Prize 22 years later, but that's okay. People do get Nobel Prizes long time after they have done the job. But it was a bit of a tragic situation because Landau was actually in a deep coma at that time. He had met with a car accident in 1960, and for 2 years he was in a coma, and nobody was sure whether he would survive. In fact, the Nobel Committee actually hurried up and gave him the Nobel Prize that year because they were not sure that he would survive beyond that year. And as you know, Nobels are not given posthumously. So they were afraid that if they waited for another year, Landau might die, and somebody as important as Landau would not get a Nobel Prize. So he was given a Nobel Prize not after death. Of course, nobody is given Nobel Prize after death. But he was given a Nobel Prize at a time when he was almost near death. He did manage to survive. Okay, that was touted as one of the greatest success stories of Russian medicine. And the Russians actually tried to show that their medicine is much superior than the West by publicizing this a lot, that they managed to actually save Landau's life, although he never managed to actually come back to active physics after that. And he died a few years later from these injuries. So he came out of the coma, survived for 4 or 5 years, died after that. And well, he may not have enjoyed the fact that he was given the Nobel Prize for superfluidity, because in his own opinion, many of his other works were more important. But anyway, that was a sort of tragic end to the story. Okay, we'll talk about the theory in detail and Landau's work, the actual theoretical work beyond the critical velocity in the next class. And let me just say it bye for today.